Hello and welcome to the Wave Interference Virtual Lab. I'm going to dive right in and go pretty quickly through each of the changes that are listed on your worksheet. So be prepared to pause this video in order to give yourself time to really examine what's going on the screen and think through and write down your answers. Okay, so the first question is, before you change any settings, describe the shape and motion of the water waves being produced by the dripping faucet. So you can draw what you see here in the tank. And let me just say that I'm going to be calling this a tank, but really if this tank were as shown with 4 sides and just this little square, you would have waves being reflected off all of the 4 sides, and it would be kind of crazy. So really this is kind of like a huge ginormous pool, which you only have one little window here of, because right now you can see the waves, they just continue off forever. Later on we're going to be adding things that will create some wave reflections, but for right now when I refer to tank, I'm really saying this little window we have on our waves that are being created by the faucet. Okay, so you can use words or you can draw what you see here, but do indicate the shape and the direction that the waves are moving. Now I'm going to turn on show the graph. Okay, and notice that this dotted line across the middle of the tank here is what is being registered or drawn here on the graph. Okay, so we have this feature where we could turn the tank on its side, and you would actually see, if you were looking right in the middle of that tank, these water waves being produced, which mirror the graph down below. Okay, but for right now, think through what the brightest areas of the tank represent. This is number 2 on your worksheet. I'm going to pause this and then I'll just advance it. Okay, so right here, what we have aligned to the bottom of this wave is the dark area, which is question number 3. So what do we call the lowest part of a wave? That would be your answer for number 3. I'm going to advance it some more and we'll see where the screen in the tank is the brightest. Right here where the water is dripping at this point is going to be the top of a wave. So what do we call that top of a wave? That's question number 2 on your worksheet. Okay, now I'm going to move the amplitude all the way to max it out, and I want you to look at how things change on the graph as well as how things look different in the tank. Okay, and make those observations and write them down for question number 4. Now I'm going to turn the water off and add a wall. And this wall will create a barrier that ripples the waves will bounce off of or reflect off of. Okay, now I'm going to just let one drip come down. I want you to watch the wave, watch the direction it travels, and then the direction that the reflected wave travels, and then draw the shape and the orientation of the reflected wave in the tank. On your worksheet, there's already a little wall drawn. So I'll give you another pulse here. And you want to draw what you see in the tank, not on the graph. Okay, just show that one wave, how it looks when it's reflected back off the wall. Now on the next page, think about how that reflected wave compares to the incident wave, the original incoming wave as it approaches the wall. I'll give you a couple other pulses, but Not all of these things will change. Some of them stay the same, but some of them do change. So does the direction of travel change? Does the speed at which the wave is moving through the water change when it gets reflected? Is the shape change? Or the orientation? Maybe the shape is the same, but it's rotated a certain number of degrees in a different direction. Now, one thing that's not talked about on the worksheet here, but if we have a slanted surface and a wave approaches it, notice how that affects things. This is something hopefully that we did in lab. If you remember, the law of reflection states that the angle of the incident wave will equal the angle of the reflected wave. Okay. Now, number 7 asks you to compare these waves here, this single wave that's reflected back, to the beads on a string sim that was in your reading. If you haven't done your reading yet, go and do that now. It will really help you with this worksheet. And if you skip that reading, you're going to miss out on a lot of really important information that you'll need to know moving forward. Okay, so when you were instructed in your reading to do one single pulse with the beads on a string, and that pulse was reflected back through the string, you saw the reflected wave was different in some way to the incident wave. And in a similar way, this reflected wave is different than the incident wave. Write that down for number 7, how those two are either similar or different. Okay, now I'm going to adjust the frequency to maximum and turn this on. And notice that as those reflected waves move back through the tank, they combine or interfere with the incident waves and form a pattern. Okay, question 8 asks, what do you think the fuzzy grayish areas represent? One way you can kind of get some more information is by pausing here. And I'll try and pause it so that there's a gray fuzzy area right here in the middle of the dotted line, so it shows up on the graph. Okay, so where it's the fuzziest gray, what's happening to the wave? Write that down for number 8. Yeah, I'm going to remove this barrier. I'm going to grab a second faucet here. And now we have 2 sources of waves. And those waves again are going to combine, they're going to interfere with each other, and some of the wave peaks are going to meet with some of the wave troughs and cancel each other out, and some of the peaks are going to combine with other peaks and make even greater waves. So there could be some destructive and constructive interference going on. So let me pause it, and you can, for number 9, draw the pattern that you see. And you want to draw the circles, but also make sure you draw these fuzzy rays, these fuzzy gray lines that we call rays, that represent areas of destructive interference, right? Oh, I think I just gave you the answer for number 10. Number 10 asks, what do you think is happening along the fuzzy gray lines that radiate out from the faucet? Okay, let me add a detector here. Okay, this enables you to place the detector anywhere in the tank. You're not limited to just the center line here. And it shows you a graph, so I can actually hover over one of these fuzzy gray lines and see that the amplitude is a lot less, almost a straight line in some areas. Okay, there it's really small amplitude. Right next door, there's a larger amplitude. Okay, Moving on to the next page, number 11. How many rays, those gray fuzzy lines radiating out from the faucets, do you see? Okay, so at this point, I would say there's 1, 2, 3, 4, 5, 6, 7, 8 really distinct rays. This part here and this part here, those could be, but we're not going to count those right now. We're just going to look at these ones that are really thin and distinct. Okay. Now I'm going to adjust the frequency, turn it down a little bit, and see how that changes the pattern. Okay. Now I turn the frequency down about 1/4, and now we have 1, 2, 3, 4, 5, 6 rays. Let's set it to about halfway. Let things calm down a little bit. Now we only have 1, 2, 3, 4 rays. Okay, so number 12 asks, how does the drip frequency relate to the number of rays, the number of destructive interference points as these waves are interacting and traveling through the ripple tank? Right, I'm going to get things set up for the next section where we are adding a 1-slit barrier. Right, and things have settled down now, so you can notice how the gap creates a new wave pattern that bends to fill some of these areas behind the tank. Okay, so right along here on this side of the wall, all of these waves that hit this barrier are reflected back and causing constructive and destructive interference on either side. So the only waves that are really making it through are where there's this opening. But despite that, we don't have waves just going straight across. You see how they're spreading out and they're being bent into a slightly different angle here on the other side of each barrier. Also notice how this wave has a larger amplitude in the middle that rapidly decreases in magnitude to either side. Okay, so the wave has a higher amplitude. Let me get the detector out again and so we can look at it. We look right here, we've got this kind of amplitude. The farther away from the center I get, the smaller the amplitude is. Okay, we can go here. And also the farther away from the faucet, the lower the amplitude too, just because the waves are losing energy. But if we go the same distance away from the faucet, we're getting smaller and smaller amplitude of those diffracted waves. So take a minute and draw the pattern that you see on the screen right now. Let me pause it. It might be easier to draw when it's paused. Okay, draw what's on the left side and the right side. Don't worry about drawing the faucet or the drips. Just draw the wave pattern you see in the tank. Okay, now I'm going to adjust the frequency a few times. Let's see what happens. Pay particular attention to what's happening here on either side of the barrier and what's happening here. Okay, what do you note? What differences do you notice here? As the wavelength increases, because I'm decreasing the frequency, how does that affect the amount of diffraction on the other side of the gap? Okay, now I'm going to set my frequency to medium and make the gap smaller, about 1/2 centimeter. Now pause it. And number 15 asks you to draw the patterns you observe again on both sides of the barrier, this time with a smaller gap and a lower frequency. Because there is a relationship between wavelength and the size of the gap that the waves are moving through. So see if you can figure out just from your observations here what that relationship is. Number 16 asks, which of the following contribute to the pattern on the left side of the barrier? So circle each one that is applicable here. Are waves being reflected on the left side of the barrier? Is there wave interference? Is there constructive and or destructive interference going on the left side? If there is, circle B. And is there any diffraction going on the left side? And then number 17, answer those same questions for the right side of the barrier. Is there any reflected wave stuff going on the right-hand side? Is there any wave interference where waves are combining to either be greater or to diminish one another? And is there any diffraction going on at this point in this scenario? Okay, number 18 is just kind of a free-for-all. Since you are probably watching this because you couldn't get the sim to work, I'll just show you a few of the other features. What we have here is kind of like a sound room. So the medium now here is that the wave is moving through is not water anymore. It would be the air in the room, right? One of the cool features here is that it actually gives a little representation of the particles that are moving. The waves look very similar right now to what you would see in water waves, and we can even turn on the graph and see that the waves look really similar. Let me turn the frequency up a little bit. Okay. But now I'm going to show you what it looks like with the particles. So let's say each one of these particles represents a molecule in the air. It could be oxygen or nitrogen or whatever. Well, let me turn the frequency back down because it's easier to see. When you see a wave that moves through the room, you can kind of follow it as it moves across. It's the compression that is the wave, right? Where the molecules are closer together. And you can see that it moves to the right. You can see on the graph too that the crest of the wave, here's where the molecules are, well, here it shows where they're the farthest apart, the area of rarefaction. And then if we move forward, okay, we have a wave trough where there is an area of greatest compression. Okay, now it's fun because it's a little confusing to the eye just to follow all these little beads and see what's actually happening. But if you take one of the X's and just look at one of the X's and see what it does and how it moves. Let me turn up the frequency. It's a little hard to see still. You can see that these X's are these molecules are not, okay, it's going a little crazy because there's a new pattern here. They're just moving back and forth a little bit. They're not actually moving through the room. They're just bumping into a molecule that's nearby and transferring that energy and creating this wave that moves through the room. Okay, so sound waves. Now let's move on to light waves. Well, maybe I could do this. Maybe I could do a pulse. Maybe that's an easier way to see it move through. I don't know. It's pretty hard to see because of all these molecules. Okay, moving on to light. Okay, now the cool thing about light is, well, in this sim, they're kind of limiting us to visible light. Okay, so we can lower the wavelength and get a different color. And we have a purplish blue, okay, which is going to be a higher frequency or a smaller wavelength of light. And one of the cool features of this is that you can see it project on a screen over here, which right now is not very exciting because it's just showing that that light is being projected on this screen. But once we add a barrier, and you can see that the only light that is getting through, let me increase the amplitude so it's brighter. Okay, amplitude with sound is loudness, or how loud it sounds to our ears. Amplitude with light is seen with how bright it is. Okay, so only light is getting through this gap here, and there's not a whole lot of diffraction going on. Now let me make the slit smaller. Okay, there's a little bit of diffraction going on now. You can see instead of just light where the gap is, you're getting some diffused light on either side because of the diffraction, this bending of the light as it goes through. Now let's do 2 slits. Okay, this is where it gets kind of crazy. Because of the diffraction of light, because you have some destructive interference, when we have 2 slits that are very close together with a small wavelength of light, then you will actually start to see more. You'll see light right behind the barrier. You'll see these little bands of light. Let's see if that same thing works with a higher amplitude. Let's go back to the red. Okay, so now we have a, sorry, not higher amplitude, a larger wavelength. Okay, so we have 2 slits. We still have diffraction going on. This time we have a large diffuse area of light here, really fairly bright area of light here on the screen, and then more diffuse light over here. Okay. And that's all because of the diffraction and the wave interference that's going on. That one's really hard to see. Now we're getting into infrared, which is beyond the visible spectrum. Okay, so I'm sorry you weren't able to download this sim and play around with it on your own. It's really pretty cool, all the different things we can do with it. But hopefully you learned something from the video and were able to complete the worksheet.